Hello good day viewers. In this tutorial we are going to learn how to write a complex number in a rectangular coordinate and also in a polar coordinate. What is the difference between polar coordinate and rectangular coordinate? A rectangular coordinate or Cartesian coordinate is just a point where that complex number is located. But polar coordinate is telling us the direction towards that complex number. So it deals with angle, right? And distance. So we have three problems here, and we want to write each of these complex numbers in a rectangular coordinate, likewise in a polar coordinate. So let me write this. You know, generally this is how a complex number is written in standard form: z equal to a plus bi. This is the standard way of writing a complex number. Therefore, Cartesian coordinate or rectangular coordinate, let me write it as rectangular RC, is equal to the point A comma B, where A is the real part and B is the imaginary part. As simple as this. But polar coordinate is just what? R comma theta. R is what? Z modulus, and we have learned how to find Z modulus. It's just the distance, right? So R is equal to Z modulus. By applying Pythagoras rule, you'll be able to find this. And theta is the angle subtended while you're heading to that complex number. So now let us use this information to find the solution to these problems. So let's start with the first complex number, z1 equal to 2 plus 2 root 3i. Writing complex number in a rectangular coordinate is very simple. Rectangular coordinate, because it's something you can see, the real comma the imaginary part. As simple as this. But for the polar coordinate, you have to calculate for the distance and also for the angle subtended. So assuming this is our complex number here, which is 2 plus 2 root 3i, we are looking for the distance from the origin, that is r, and also this angle right here, theta. So we need these two to obtain our polar coordinate. By applying Pythagoras rule, you know, the imaginary part, the distance there is 2 root 3, and we have the real part, which is 2. To find r is equal to the square root of 2 squared plus 2 root 3 also squared. 2 squared is 4. 2 root 3 squared is 12, because this is 4 and this is 3. 4 times 3, 12 plus 4 is 16. Square root of 16 is 4. We are looking for only the positive value because we are talking about distance. So this is 4. But what about the angle? We have learned that this angle theta can be obtained by taking tan inverse, because you know the relationship between this. Tan is what? Opposite divided by adjacent. So this divided by this. 2 root 3 divided by 2. And 2 will cancel 2, leaving only root 3. Oh, we have tan inverse here. And tan inverse of root 3 is 60 degrees, or pi over 3, but I want it to be in degrees. So this is 60 degrees. So we have gotten our r and we have gotten our theta. So we can directly write this as PC for the polar coordinate as 4, 60 degrees. Now this is all about question number 1, that is Z1. Then moving on to the Z2. All right, as you can see, this is the second problem, but I know you may experience a glitch in the video. This is because I used the reference angle as our final theta, which is very wrong. Therefore, I have to correct the video. Okay, we have our complex number negative 2 root 3 plus 2i. So the rectangular coordinate will be what? The real part, negative 2 root 3, comma, the imaginary part. As simple as this, right? But for that polar coordinate, observe that the real part is negative, which is situated along the left-hand side. But the imaginary part is positive, so it is off here in the second quadrant, somewhere here. So we're looking for this R, likewise this angle from the standard position. So we can use this angle here as a reference, theta reference, which has the same value with the angle from the first quadrant. If you observe, this angle and this angle will be the same. So all of these are reference angles. So to find this reference angle, let us first of all find our R. You know, the imaginary part is 2 and the real part is negative 2 root 3. So R is equal to the square root of 2 squared plus negative 2 root 3 also squared. This is 12, this is 4. If you add them together, you get 16. Square root of 16 is equal to 4. Remember, we are looking for only the positive value. So therefore, the polar coordinate, we have seen that R is 4. What is left for us to find is the angle. So for our angle, since we are looking for the reference first, whatever we obtain, we have to take it away from 180 degrees. Because this is the angle we are looking for, not this one. This is just a reference angle. So theta reference or reference angle equal to tan inverse of what? 2 divided by 2 root 3. We are going to use everything positive. 2 will cancel 2. We have 1 divided by 3. If you rationalize it, you have root 3 divided by 3. And tan inverse of root 3 divided by 3 is either 30 degrees or pi by 6. But remember, we want to use in degrees, theta in degrees, right? So this is 30 degrees. If this is 30 degrees, what about the angle at the back? To find it, we have to take away this 30 from 180, which shall give us what? 150 degrees. Therefore, our main theta, which we are looking for, is 180 minus 30 degrees, which is equal to 150 degrees. Therefore, the angle here from the standard position down to this complex number is equal to 150 degrees. So this is all about question number 2. Now we can go to question number 3. The last one, we have Z3 equal to 1 minus root 3, right? Root 3i. This is our complex number. Rectangular coordinate is just what? 1 comma negative root 3. So what about the polar coordinate, which is r comma angle? First of all, let us sketch it here. Real part is positive, either in the first or in the fourth quadrant. That is where the real part is positive. But you can see the imaginary part is negative, meaning we are in the fourth quadrant. So suppose this is where our complex number is situated. We need this angle from the standard position back to this. And we need this r. So we need this theta. So why can't we just use this theta as theta r? That is reference angle. So whatever we obtain here, because it is closer to 360 degrees, we'll be able to subtract it from 360 to get the back angle. I think it will be better. So let us first of all find our r. R will be equal to, okay, I can connect this one to make our right angle triangle. The real part is 1 and the imaginary part is negative root 3. So we have square root of 1 squared plus negative root 3 squared. 1 squared is 1, negative root 3 squared is 3, 3 plus 1 is 4. Square root of 4 is 2. So r is equal to 2. The distance from this origin down to the complex number is 2 units. Then the angle, we are going to use the reference angle, assuming that we are in the first quadrant. We can use this angle. They are all the same, right? So reference theta is equal to tan inverse of root 3 divided by 1, which is the same thing as root 3. And tan inverse of root 3 is equal to 60 degrees. 60 degrees. But we are very close to 360. We just obtained this angle, but we are looking for the angle from the back, from the standard position. So if you take away 60 from 360, you'll be left with what? 300. So our main theta, let me write it here. Our main theta is equal to 360 minus 60, which is what? Equal to 300 degrees. So we have our r as 2 and theta as 300. So we have 2, 300 degrees. As simple as that. So subsequently, we are going to learn how to convert from this polar coordinate back to the Cartesian coordinate or rectangular coordinate. Suppose the complex number is not given. Maybe you are just given this one. How can we convert it back into rectangular coordinate? Thank you for watching. Do share to your learning colleagues and don't forget to subscribe to my YouTube channel for more exciting videos. Bye bye.